Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions. The features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, these bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line, but Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear, it converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis, but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible, hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors. Larger tidal forces lock a moon more quickly, closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the moon had already been showing the same face toward our planet. for billions of years. Tidal locking doesn't just affect the moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet, because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the Moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the Moon's orbital period. At that point, Earth would be tidally locked to the Moon, just as the Moon is now locked to Earth, with the same face of Earth always facing the Moon. However, this will never happen because the Sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the Moon. The expanding Sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the Moon has significant consequences for lunar exploration and observation. The far side of the Moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called Maria that dominate the near side's appearance. This asymmetry likely relates to the Moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the Moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the Moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the Moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The Moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time. Why gas giants spin at different speeds? The giant planets of our solar system rotate at speeds that seem almost impossible when you first encounter the numbers. Jupiter, the largest planet, completes a full rotation in just under 10 hours. Imagine standing on a world where a single day passes more than twice as fast as the time it takes to watch a long movie. Saturn spins even faster in some ways, though its rotation is more complex. Uranus and Neptune, the ice giants farther out, rotate at their own distinct rates, each with rotational periods that tell a story about how they formed and what has happened to them over billions of years. Picture Jupiter in your mind, a massive sphere of swirling clouds in shades of cream, brown, orange, and red. This giant world contains more mass than all the other planets combined, yet it spins so rapidly that it bulges noticeably at its equator. If you could somehow stand at Jupiter's equator, you would be moving at over 28,000 miles per hour, far faster than anything on Earth except spacecraft. The planet's day, the time it takes to complete one rotation, is only about 9 hours and 55 minutes. This incredible speed creates winds that race around the planet in alternating bands, some flowing eastward, others westward, creating the distinctive striped appearance we see in telescopes. But here's where it becomes fascinating. Not all of Jupiter spins at the same rate. The planet is made primarily of hydrogen and helium in gaseous and liquid forms, with no solid surface to anchor to. The equatorial regions spin slightly faster than the polar regions, completing a rotation in about 5 minutes less time. This differential rotation is possible because Jupiter isn't a rigid body like Earth. Different latitudes can rotate at different speeds, sliding past each other in the fluid interior. The deep interior, where hydrogen is compressed into a metallic liquid state, may rotate at yet another rate, one that scientists are still working to measure precisely. Saturn presents an even more puzzling picture. This ringed giant is less dense than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, with a day lasting only about 10 hours and 33 minutes, causes an even more pronounced equatorial bulge than Jupiter's. The planet's diameter at the equator is nearly 10% larger than its diameter from pole to pole. Picture a sphere that's been squeezed from the top and bottom while being stretched around its middle, all due to the centrifugal force of its rapid spin. What makes Saturn particularly mysterious is that determining its exact rotation rate has proven remarkably difficult. Unlike rocky planets, which have surface features that can be tracked, or planets with strong magnetic fields that rotate with the deep interior, Saturn presents challenges. Its magnetic field is almost perfectly aligned with its rotation axis, which makes it hard to use as a reference. Different methods of measuring Saturn's rotation have given different results, sometimes varying by as much as several minutes. The planet's atmosphere rotates at different speeds at different latitudes, just like Jupiter's. But figuring out the rotation rate of Saturn's deep interior, the true rotation rate of the planet, remains one of the ongoing puzzles in planetary science. The rings of Saturn add another layer to this story. These rings are made of countless particles of ice and rock, each one orbiting Saturn independently, according to the laws of orbital mechanics. The inner parts of the rings orbit faster than the outer parts, completely independent of how fast the planet itself spins. If you could watch from above Saturn's North Pole, you would see the rings spinning like a vast flat disk, while beneath them the planet rotates at its own separate rate. And within the planet, different layers rotate at their own speeds as well. Now travel farther out to Uranus, the tilted giant. This planet rolls through space like a ball rolling along the ground, with its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Something in Uranus's past, likely a massive collision with another planet-sized object, knocked it onto its side. Despite this dramatic tilt, Uranus rotates relatively quickly, completing one rotation in about 17 hours and 14 minutes. This is slower than Jupiter and Saturn, but still far faster than Earth's 24-hour day. The interior structure of Uranus affects its rotation in ways different from the gas giants. Uranus is classified as an ice giant rather than a gas giant because, beneath its hydrogen and helium atmosphere, it contains a much larger proportion of water, methane, and ammonia ices. These materials, compressed under tremendous pressure, create a layered interior that may not mix as freely as the interiors of Jupiter and Saturn. This layering could mean that different depths within Uranus rotate at substantially different rates, though our knowledge of the planet's interior remains limited from Earth. Neptune, the farthest giant planet, spins with a period of about 16 hours and 6 minutes, slightly faster than Uranus, despite being similar in size and composition. Neptune's deep blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Like the other giant planets, Neptune shows differential rotation, with its equatorial atmosphere moving at a different speed than the atmosphere at higher latitudes. The planet has the strongest winds in the solar system, with some storms showing wind speeds exceeding 1,200 miles per hour. These winds don't simply follow the rotation of the planet. They race around at speeds that are faster than the underlying rotation rate, driven by heat flowing from Neptune's interior. The question of why these giants spin at such different speeds takes us back to the formation of the solar system. Imagine the early solar system as a vast rotating disk of gas and dust surrounding the young sun. Within this disk, material began to clump together, forming the seeds of planets. As these clumps grew larger through gravity, pulling in more material, they began to spin faster due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms in. Each growing planet accumulated material that was already moving in orbit around the Sun. This material had angular momentum, and as it fell onto the growing planet, it transferred that momentum to the planet itself. The amount of spin the planet ended up with depended on exactly how this accretion process occurred, the trajectories of the infalling material, the timing of impacts, and whether the material came in symmetrically or from preferred directions. Jupiter and Saturn, being closer to the Sun and in regions with more available material, grew faster and larger than Uranus and Neptune. Their rapid growth meant they could capture enormous amounts of gas from the protoplanetary disk before it dissipated. This gas fell onto the planets from all directions, and the net effect was to spin the planets up to high rotation rates. The exact speed depended on the complex details of how the gas flowed onto the growing planet and how the planet's gravity interacted with the surrounding disk. The spin rates were also affected by large impacts during the final stages of planet formation. When planet-sized objects collided, they didn't just add their masses together, they also exchanged angular momentum. The angle and speed of impact determined whether the collision would speed up the planet's rotation, slow it down, or even change its axis of rotation. Uranus's extreme tilt almost certainly resulted from one or more giant impacts that occurred late in its formation. Inside these spinning giants, the story continues. The rapid rotation creates strong Coriolis effects that organize the atmospheric flows into bands and zones. Rising warm gas gets deflected by the planet's rotation, creating the jet streams that race around the planets at different latitudes. In Jupiter's case, these jets are remarkably stable, maintaining the same patterns for centuries or longer. The rotation also affects the planet's magnetic fields, which are generated by the movement of electrically conducting fluids in their interiors, liquid metallic hydrogen in Jupiter and Saturn, and perhaps ionic water solutions in Uranus and Neptune. The differential rotation, the fact that different parts of these planets spin at different rates, creates zones of shearing where adjacent layers of fluid slide past each other. These shear zones can become unstable, spawning turbulence and storms. The Great Red Spot on Jupiter, a storm larger than Earth that has persisted for centuries, exists in a region where different wind speeds interact. The storm itself rotates, but at a rate different from the planet's overall rotation, caught in a complex interaction between different atmospheric layers. As these planets continue their journeys around the Sun, their rotation rates change, though extremely slowly. Gravitational interactions with their moons cause tidal effects that gradually transfer angular momentum between the planet and its satellites. This process is the same one that has locked our moon so that it always shows the same face to Earth, though it operates much more slowly on the giant planets due to their enormous masses. Jupiter's large moons are very gradually moving away from the planet, carrying angular momentum with them, which means Jupiter's rotation is slowing down. But this process operates over timescales of billions of years. The interiors of these planets remain largely mysterious, hidden beneath thousands of miles of atmosphere and fluid layers. Scientists use the planet's rotation rates, combined with precise measurements of their gravitational and magnetic fields, to deduce what must be happening in the unseen depths. The exact rotation rate of the deep interior tells us about the distribution of mass within the planet and how rigidly different layers are coupled together. Variations in the gravity field, measured by spacecraft flying past, reveal how mass is distributed between the equator and the poles, which in turn reveals how the rotation has shaped the planet's interior structure. Each of these giant worlds continues to spin through the darkness of space, their days flashing by in fractions of an Earth day, their atmospheres swirling in patterns that have persisted for eons. The differences in their spin rates encode the history of the solar system's formation, the random chance of ancient collisions, and the ongoing physical processes that govern how fluids behave under extreme conditions of pressure, temperature, and rotation. Understanding why gas giants spin at different speeds means understanding not just these four worlds, but the principles that govern planetary formation and evolution throughout the universe, wherever giant planets circle other stars. Why some planets have no moons. Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers, but these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the Sun, or get ejected from the system entirely. The closer the planet is to the Sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are three primary mechanisms: co-formation, where the moon forms from the same disk of material as the planet; capture, where the planet's gravity snares a passing object; and giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon, or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter. Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across, and Deimos about 12 kilometers. Mars likely captured them during the early solar system, when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely form their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young Sun. These disks contained enough material to form multiple large moons. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons, moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. Why stars explode when they die? For millions or billions of years, a star exists in a state of perfect balance. Gravity pulls inward, trying to compress the star, while the heat and pressure from nuclear fusion in the core push outward, resisting that compression. This equilibrium, this careful balance between opposing forces, allows stars to shine steadily for incomprehensible stretches of time. But eventually, inevitably, the fuel runs out. For some stars, death comes quietly, a gentle fading as they shed their outer layers and cool into obscurity. But for the most massive stars, death is anything but peaceful. When these giants exhaust their nuclear fuel, they don't fade. They explode with such violence that a single dying star can briefly outshine an entire galaxy of hundreds of billions of stars. The path to a supernova explosion begins with the structure of massive stars and how they generate energy. Stars like our Sun fuse hydrogen into helium in their cores, a process that releases energy and provides the outward pressure needed to support the star against its own gravity. But massive stars, those with at least 8 times the Sun's mass, don't stop at hydrogen fusion. When the hydrogen in the core is exhausted, the core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. This is just the beginning. For massive stars, nuclear fusion proceeds through multiple stages, each burning a different fuel. After helium burning comes carbon burning, then neon burning, then oxygen burning, and finally silicon burning. Each stage produces heavier elements as its ash, and those ashes become the fuel for the next stage. Each stage also burns faster than the previous one because it occurs at higher temperatures and releases less energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The star develops a layered structure, like an onion, with each shell fusing a different element. The outermost layers still contain mostly hydrogen. Deeper in, a shell fuses helium. Deeper still, shells fuse carbon, neon, oxygen, and silicon in succession. At the very center lies an iron core, about 1.5 times the mass of the Sun, but compressed into a sphere roughly the size of Earth. This iron core is the end of the line. Iron occupies a special place in nuclear physics. Elements lighter than iron release energy when fused together. This is what powers stars. Elements heavier than iron release energy when split apart through fission, but iron sits at the peak of the binding energy curve. Fusing iron nuclei together doesn't release energy, it requires energy. The iron core cannot generate heat through fusion. It's an inert ball of matter, supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons being compressed too closely together. The iron core grows as the silicon-burning shell above it continues converting silicon into iron. Each second, tons of iron are added to the core. The core is already incredibly dense, about 10 billion kilograms per cubic meter, and as it grows more massive, it also grows hotter and denser. The electrons supporting the core are squeezed into higher and higher energy states, reaching energies where they can do something remarkable. They can merge with protons. This process, called electron capture or inverse beta decay, occurs when an electron is forced into a proton, creating a neutron and releasing a neutrino. The neutrino immediately escapes from the star at the speed of light, carrying energy away. This removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core contracts further, squeezing more electrons into protons, creating more neutrons, removing more pressure support, causing further contraction. This runaway process accelerates catastrophically. Subrahmanyan Chandrasekhar calculated in the 1930s that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses, now called the Chandrasekhar limit. When the iron core exceeds this limit, electron degeneracy pressure can no longer hold it up. The core collapses. What happens next occurs in less than a second, but releases more energy than the star produced during its entire multi-million-year lifetime. The core implodes at velocities reaching 70,000 kilometers per second, nearly 1/4 the speed of light. The outer part of the core falls onto the inner part, compressing it to densities exceeding that of atomic nuclei. At these densities, around 400 trillion grams per cubic centimeter, nuclear forces become repulsive rather than attractive. The collapse halts suddenly, like a ball hitting a concrete floor. The abrupt halt of the inner core creates a shock wave that propagates outward through the infalling material. This bounce shock wave contains enough energy to blow apart the entire star, but calculations show that it stalls within milliseconds, unable to push through the still infalling outer layers. For decades, this posed a major theoretical problem. How do stars actually explode if the bounce shock stalls? The answer lies in neutrinos. During the collapse, protons and electrons combine to form neutrons, releasing vast numbers of neutrinos. The newborn neutron star at the core, incredibly hot, temperatures exceeding 100 billion degrees, produces additional neutrinos through various processes. In normal circumstances, neutrinos barely interact with matter. Trillions pass through your body every second from the sun without causing any effect. But the matter in a collapsing stellar core is so dense that even neutrinos can't escape immediately. They diffuse outward over several seconds, and during this time, a tiny fraction, less than 1% of them, interact with the infalling material. This sounds negligible, but the total neutrino energy is staggering, about 10 to the 53 ergs, roughly 100 times the energy the Sun will radiate during its entire 10 billion year lifetime, released in just 10 seconds. Even if only 1% of this energy couples to the stellar material, it's more than enough to revive the stalled shockwave and drive the explosion. The outer layers of the star are blasted into space at speeds of 30,000 kilometers per second or more. This core collapse supernova, designated Type 2 if hydrogen is present in the spectrum, or Type 1b or IC if the star lost its hydrogen envelope before exploding, is the fate of all massive stars. The explosion is so energetic that it creates elements heavier than iron through rapid neutron capture. During the few seconds of the explosion, neutrons are so abundant that nuclei can capture many neutrons in quick succession, building up elements like gold, platinum, and uranium that cannot be created through normal stellar fusion. Every atom of gold in existence was created in supernova explosions or in the mergers of neutron stars. The only direct detection of supernova neutrinos occurred on February 23, 1987, when neutrino detectors on Earth registered a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The neutrinos arrived about 3 hours before the light became visible, exactly as predicted. The neutrinos escaped during the core collapse, while the light had to wait for the shockwave to reach the star's surface. This detection confirmed the core collapse mechanism and marked the beginning of neutrino astronomy. There's another type of supernova with a completely different mechanism, the Type 1a supernova. These occur in binary star systems, where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, carbon fusion ignites throughout the entire white dwarf, almost simultaneously, not gradually, from the center outward. The fusion releases so much energy that the white dwarf is completely disrupted. There's no neutron star remnants left behind. The entire star is blown apart. Type Ia supernovae are remarkably uniform in their energy output because they always occur at approximately the same mass, the Chandrasekhar limit. This uniformity makes them valuable as standard candles for measuring cosmic distances. Observations of distant Type Ia supernova by Saul Perlmutter, Brian Schmidt, Adam Ress, and their teams in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and earning the observers the 2011 Nobel Prize in Physics. The energy released in a supernova is distributed across different forms. About 99% goes into neutrinos, which escape into space carrying information about the core collapse. About 1% goes into kinetic energy of the ejected material, the blast wave that expands into space. Only about 0.01% goes into light, but this is still enough to make the supernova visible across billions of light years. For a few weeks, a single supernova can outshine its entire host galaxy. The remnant left behind after a core collapse supernova depends on the core's final mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure succeeds in halting the collapse, creating a neutron star. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot stop the collapse, and the core continues collapsing into a black hole. The exact threshold remains uncertain because it depends on the equation of state of nuclear matter at extreme densities, which is not precisely known. Supernova explosions enrich the interstellar medium with heavy elements, The carbon, oxygen, silicon, and iron in the ejected material mix into interstellar gas clouds, raising their metallicity, the abundance of elements heavier than hydrogen and helium. These enriched clouds eventually collapse to form new generations of stars and planets. The Sun and Earth formed from material enriched by previous supernova. Every element heavier than lithium in your body was created in a star and dispersed by a supernova or stellar wind. The shockwave from a supernova can trigger new star formation by compressing nearby molecular clouds. The expanding remnant, a shell of hot gas and energetic particles, can remain visible for thousands of years. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that occurred in 1054 AD and was recorded by Chinese astronomers. At its centre sits a rapidly spinning neutron star, a pulsar rotating 30 times per second, powered by the rotational energy it inherited from the collapsed core. Supernova rates in galaxies depend on the star formation rate and the mass distribution of stars being formed. The Milky Way experiences roughly 2 to 3 supernovae per century on average, though we haven't witnessed a nearby visible supernova since Kepler's supernova in 1604. Most occur hidden behind dust in the galactic plane, their light obscured but their effects, shockwaves, cosmic rays, heavy element enrichment, rippling through the galaxy. The most massive stars can experience even more exotic deaths. Stars exceeding roughly 130 solar masses might become pair instability supernovae, where gamma rays in the core become so energetic that they spontaneously convert into electron-positron pairs. This removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is destroyed. No remnant of any kind survives. Stars more massive still might collapse directly into black holes without exploding at all, with all their mass disappearing behind an event horizon in silence. Understanding why stars explode when they die connects nuclear physics, quantum mechanics, general relativity, and hydrodynamics. It explains the origin of elements, the formation of neutron stars and black holes, the enrichment of galaxies with heavy elements, and the triggering of new star formation. The death of massive stars through supernova explosions is not just destruction, it's creation, recycling stellar material back into space, enriched with new elements, ready to form new stars, new planets, and perhaps new life, continuing the cosmic cycle that has built the complex, element-rich universe we inhabit today, all initiated by the catastrophic collapse that occurs when fusion finally fails and gravity wins its ultimate victory over the force that gave the star life. Why some asteroids are made of metal? Most asteroids are dark, rocky bodies composed of silicate minerals similar to the rocks found on Earth's surface. But among the hundreds of thousands of asteroids orbiting in the main belt between Mars and Jupiter, a small population stands out as fundamentally different. These are the metallic asteroids, composed primarily of iron and nickel rather than rock. They gleam brightly in reflected sunlight, their surfaces shining with the luster of exposed metal. The most famous of these is Psyche, a massive asteroid about 226 kilometers in diameter that appears to be almost entirely metallic. Understanding why some asteroids are made of metal means understanding the violent history of the early solar system and the process by which planets form their layered structures of core, mantle, and crust. The story of metallic asteroids begins with planetary differentiation, the process by which a planetary body separates into layers based on density. When a planet or large asteroid forms, it starts as a mixture of materials, rock-forming elements like silicon, oxygen, magnesium, and calcium mixed with metallic elements like iron and nickel. If the body grows large enough and contains enough radioactive elements, it heats up from the decay of radioactive isotopes and from the energy of continued impacts as it accretes more material. When the temperature rises above the melting point of iron, about 1538 degrees Celsius, something dramatic happens. The iron, being denser than the surrounding silicate rock, begins to sink toward the center of the body. This process, called the iron catastrophe, releases enormous amounts of gravitational potential energy as the dense metal falls inward, further heating the body. The result is a differentiated structure with a dense iron-nickel core at the center, surrounded by a rocky mantle of lighter silicate minerals, and potentially a thin crust at the surface. This is the same basic structure that Earth possesses, an iron-nickel core containing about 32% of Earth's mass, surrounded by a silicate mantle and crust. Planetary differentiation occurred in the early solar system in bodies large enough to melt their interiors. Earth differentiated, Mars differentiated, Venus almost certainly differentiated. Even some large asteroids, like Vesta, which has a diameter of about 525 kilometers, underwent differentiation. Vesta has a basaltic crust formed from volcanic activity, indicating that it once had a molten interior with a metallic core. The asteroid Ceres, the largest object in the asteroid belt, at about 940 kilometers in diameter, shows evidence of differentiation as well. Once a body has differentiated into core, mantle, and crust, it becomes vulnerable to catastrophic disruption. The early solar system was a chaotic place, filled with planetesimals, asteroid-sized objects, colliding frequently as they orbited the young sun. Computer simulations of this period show that collisions were not just common, but inevitable. Some collisions led to accretion, with two bodies merging to form a larger one, but others were catastrophically disruptive, shattering one or both bodies into fragments. When a differentiated planetesimal is shattered by a sufficiently energetic collision, the fragments don't all have the same composition. Pieces from the core are metallic, pieces from the mantle are rocky, pieces from the crust might be volcanic basalts if the body had volcanism. These fragments become separate asteroids, each one representing a sample of a specific layer from the parent body. This is why we find three distinct types of asteroids in the main belt. C-type asteroids, which are carbonaceous and primitive, never having melted. S-type asteroids, which are stony and represent crustal and mantle material. And M-type asteroids, which are metallic and represent exposed cores. The M-type designation comes from their metallic composition, though determining composition from Earth requires spectroscopic analysis and radar observations. M-type asteroids are typically much more reflective than rocky asteroids. Their albedo, or reflectivity, ranges from about 10 to 18%, compared to 3 to 7% for dark carbonaceous asteroids. This high reflectivity occurs because metal reflects light efficiently compared to dark silicate minerals. The spectroscopic signatures of M-type asteroids show features consistent with iron and nickel, though definitively confirming their composition requires spacecraft missions or detailed radar studies. Radar observations provide particularly strong evidence for the metallic nature of M-type asteroids. Radio waves reflect differently from metal surfaces than from rocky surfaces. Metal is a much better radar reflector, and radar polarization measurements can distinguish metallic from rocky compositions. Studies using the Arecibo Observatory and Goldstone Solar System radar have confirmed that many M-type asteroids have radar properties consistent with metallic surfaces, supporting the interpretation that they're exposed planetary cores. The asteroid Psyche represents the most studied example of a metallic asteroid and the target of NASA's Psyche mission, launched in 2023 and scheduled to arrive at the asteroid in 2029. Psyche is unusual even among M-type asteroids because of its enormous size and apparently high metal content. If Psyche is indeed the exposed core of a differentiated planetesimal, it would be the only core of a planetary body that humans have ever been able to study directly. Earth's core lies 2,900 kilometers beneath the surface, completely inaccessible. Mars's core is similarly hidden, but Psyche's core is exposed, available for investigation. The composition of metallic asteroids reflects the composition of planetary cores more generally. Iron and nickel are the dominant elements, present in roughly the same proportions found in iron meteorites that fall to Earth, about 90% iron and 10% nickel, though with some variation. These proportions match what cosmochemical models predict for the cores of terrestrial planets. Additional elements found in smaller quantities include cobalt, phosphorus, sulfur, and carbon. Some models suggest that planetary cores might contain significant amounts of lighter elements, like silicon or oxygen, dissolved in the molten metal, but whether these would be retained in a fragmented, solidified core like Psyche remains uncertain. The value of metallic asteroids extends beyond scientific interest. These asteroids contain enormous quantities of valuable metals. A single metallic asteroid a kilometer across might contain more platinum group metals than have ever been mined on Earth. The asteroid 16 Psyche, if it's as metallic as estimates suggest, would contain iron alone worth quadrillions of dollars at current prices. Though of course, actually mining and returning such quantities would crash commodity markets and is far beyond current technological capabilities. Nevertheless, the concept of asteroid mining has captured imaginations and may become economically viable in the future as space access costs decrease and in-space manufacturing develops. Not all M-type asteroids are metallic, which complicates the picture. Some asteroids classified as M-type, based on their reflectivity and spectroscopic properties, might actually be enstatite chondrites, a rare type of rocky meteorites with high reflectivity, or other unusual rock types that mimic the appearance of metal. This demonstrates the difficulty of determining asteroid composition remotely. Only with spacecraft missions, sample return, or eventually human exploration can we definitively establish what these objects are made of. The formation of metallic asteroids also constrains the timing and locations of planet formation in the early solar system. Differentiation requires heating, which comes primarily from radioactive decay of short-lived isotopes like aluminum-26, which has a half-life of only 717,000 years. For aluminum-26 to provide significant heating, the planetesimal must form within a few million years of the solar system's birth, while aluminum-26 is still abundant. This timing constraint suggests that the parent bodies of metallic asteroids formed quickly, within the first few million years of solar system history. The subsequent disruption of these differentiated bodies likely occurred during a period of intense bombardment, possibly associated with dynamical instabilities in the giant planet's orbits. The Nice model, named after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration and later migrated to their current orbits. This migration scattered planetesimals throughout the solar system, dramatically increasing collision rates and leading to the disruption of many differentiated bodies. The timing of this instability, estimated at around 600 to 800 million years after the solar system formed, would have been late enough for the large planetesimals to have already cooled and solidified after their differentiation. Iron meteorites that fall to Earth are fragments of metallic asteroids, providing samples we can study in laboratories. These meteorites show distinctive crystalline structures called Widmanstätten patterns, interlocking crystals of two different iron-nickel alloys, camosite and taenite, that form only when molten metal cools extremely slowly over millions of years. The size and structure of these crystals reveal the cooling history of the parent body's core. Some iron meteorites cooled at rates of only a few degrees Celsius per million years, consistent with cooling in the interior of a body tens to hundreds of kilometers in diameter, exactly the size of the differentiated planetesimals that became the parent bodies of metallic asteroids. The Widmanstätten patterns become visible when iron meteorites are cut, polished and etched with acid. The two iron-nickel alloys etch at different rates, revealing the crystalline structure. These patterns are beautiful and distinctive, and they can only form under the pressure and temperature conditions found deep within planetary cores, providing strong evidence that iron meteorites, and by extension metallic asteroids, genuinely represent fragments of ancient planetary cores. The distribution of metallic asteroids in the asteroid belt provides additional clues about the formation and evolution of the solar system. M-type asteroids are found throughout the main belt, but are somewhat more common in the middle regions. This distribution might reflect where conditions were favourable for forming large, differentiated planetesimals, and where subsequent collisions occurred that could disrupt them. The relative scarcity of metallic asteroids compared to rocky ones, M-types represent only about 5 to 10% of asteroids. Makes sense given that a differentiated body's core contains much less volume than its mantle and crust combined. Some metallic asteroids might not be fragments of differentiated bodies at all, but could have formed through different processes. Certain types of impactors, if they struck at very high velocities, could strip away a body's mantle and crust while leaving the core relatively intact. Alternatively, some metal-rich asteroids might have formed from material that was already enriched in metals during the solar system's formation, though this seems less likely given what we know about how materials were distributed in the protoplanetary disk. The Psyche mission will answer many questions about metallic asteroids when it arrives at its target. The spacecraft will map Psyche's surface in detail, measure its gravity field to determine how mass is distributed internally, study its magnetic properties to search for evidence of an ancient magnetic field that might have existed when the core was still molten, and analyze its composition using spectrometers and cameras. These measurements will reveal whether Psyche is indeed a nearly pure metallic core, as many scientists suspect, or whether it has a more complex structure with rock mixed in or covering parts of the surface. Understanding metallic asteroids means understanding planetary cores, the process of differentiation, the violence of the early solar system, and the building blocks from which planets formed. Every metallic asteroid is a window into planetary interiors, exposing material that would otherwise remain forever hidden beneath thousands of kilometers of rock. These fragments of ancient cores, forged in the heat of differentiation and revealed by catastrophic collisions, represent some of the oldest processed materials in the solar system. Samples of the massive bodies that either grew into planets or were destroyed in the chaos of planetary formation, leaving behind their metallic hearts orbiting the sun as testament to the violent processes that shaped our cosmic neighborhood billions of years ago. Why space is nearly empty? When you look up at the night sky, space appears crowded with stars, planets, and galaxies. Photographs from telescopes show spectacular images of colorful nebulae, dense star clusters, and brilliant galaxies packed with hundreds of billions of stars. These images create an impression of a cosmos teeming with matter, a universe filled to the brim with celestial objects. But this impression is profoundly misleading. Space is almost unimaginably empty. The distances between objects are so vast and the objects themselves so small relative to those distances that if you could somehow travel to a random location in the universe, the overwhelming likelihood is that you would find yourself surrounded by nothing. No stars, no planets, no gas, no dust, for distances stretching farther than you could travel in a lifetime, even at the speed of light. To understand just how empty space is, consider the space between Earth and the Moon. The Moon orbits at an average distance of about 380,000 kilometers from Earth. That's far enough that you could fit all the other planets in the solar system side by side in the gap between Earth and the Moon, with room to spare. Now imagine taking a sphere with a radius equal to this Earth-Moon distance. Within that enormous volume, there are only two objects of any significant size, Earth and the Moon themselves. Everything else is emptiness, with only occasional atoms of gas or tiny dust particles scattered throughout. The situation becomes even more extreme when you consider the space between planets. Earth orbits about 150 million kilometers from the Sun. Mars orbits about 230 million kilometers from the Sun. The distance between Earth and Mars varies as both planets orbit, but at their closest approach, they're separated by about 55 million kilometers. This vast gulf contains essentially nothing. No planets, no moons, just a scattering of asteroids so small and so far apart that even if you were travelling through this region, you would be extraordinarily unlikely to come anywhere near one. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spaceships must carefully navigate, is in reality astonishingly sparse. The belt contains hundreds of thousands of asteroids larger than 1 kilometer across and millions of smaller ones. This sounds like a lot, and by the standards of everyday experience it is. But these asteroids are spread across an enormous volume of space, a region extending from about 300 million kilometers to 500 million kilometers from the Sun, and spanning the full circumference around the Sun at these distances. The result is that the average distance between asteroids is measured in millions of kilometers. If you were to travel through the asteroid belt, you would see nothing for days or weeks of travel before coming near even a single asteroid. The density of matter in the asteroid belt averages far less than 1 particle per cubic kilometer. Compare this to air at sea level on Earth, which contains about 10 to the 25th particles per cubic kilometer, a 1 followed by 25 zeros. The asteroid belt, despite containing countless asteroids, is millions of billions of times less dense than the air you're breathing right now. Every spacecraft we've sent through the asteroid belt, and many have made the journey, has passed through without incident, without needing to dodge asteroids, simply because the belt is so incredibly empty. Beyond the planets, the emptiness becomes even more profound. The nearest star to our Sun, Proxima Centauri, lies about 40 trillion kilometers away, a distance so vast that light, travelling at 300,000 kilometers per second, takes over 4 years to cross it. If you scaled the Sun down to the size of a basketball, Earth would be a grain of sand orbiting about 25 meters away, and Proxima Centauri would be another basketball more than 6,000 kilometers away. The sphere of space between these two basketballs contains essentially nothing. No planets, no asteroids, no comets that we know of, just occasional atoms of hydrogen, some dust particles so rare you could travel for years without encountering one, and the faint pressure of starlight. This interstellar space contains gas, but calling it gas seems almost misleading given its extreme tenuousness. In the space between stars, the density averages about 1 atom per cubic centimeter. For comparison, air at sea level contains about 10 to the 19th atoms per cubic centimeter. Interstellar space is less dense than air by a factor of 10 million trillion. The best vacuum we can create in laboratories on Earth, in the most sophisticated vacuum chambers, is still millions of times denser than the average density of interstellar space. Even the densest regions of interstellar space, the molecular clouds where stars form, are extraordinarily sparse by terrestrial standards. These clouds, which appear dark and opaque in photographs because they block light from stars behind them, contain perhaps 1 million atoms per cubic centimeter at their densest cores. This is dense for space, but it's still 10 trillion times less dense than air on Earth. You could travel through the densest part of a molecular cloud and not even notice. There would be no resistance to your motion, no sense of passing through anything. The emptiness extends to larger scales as well. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with vast quantities of gas, dust, and dark matter. Yet these hundreds of billions of stars occupy a disk about 100,000 light-years across and roughly 1,000 light-years thick at the Sun's location. The stars are so far apart that if you were to travel to a random location within the galaxy, you would find yourself in interstellar space, far from any star. The average distance between stars is about 5 light-years. At the scale where stars are separated by light-years, the stars themselves, objects typically about 1 million kilometers across, are essentially point-like. They occupy a negligible fraction of the galaxy's volume. Between galaxies, the emptiness reaches its most extreme. The space separating galaxies is called intergalactic space, and it's even emptier than interstellar space. The density of matter in intergalactic voids, the enormous empty regions between galaxy clusters, is approximately 1 atom per 10 cubic meters. Think about that. You could take a cube of space 10 meters on each side, large enough to contain a small house, and on average, it would contain just one single atom. This is as close to perfect vacuum as nature achieves anywhere in the universe. The scale of intergalactic distances staggers comprehension. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, lies about 2.5 million light-years away. The space between our galaxy and Andromeda is largely empty, except for a few dozen small dwarf galaxies and some scattered gas clouds. Beyond our local group of galaxies, the distances grow even more immense. The Virgo cluster of galaxies, which contains thousands of galaxies, lies about 50 million light-years away. The space between galaxy clusters is measured in tens of millions to hundreds of millions of light-years, and it contains essentially nothing. So why is space so empty? The answer lies in how the universe evolved after the Big Bang. In the earliest moments, the universe was actually extremely dense. All matter and energy were compressed into a tiny volume. But the universe has been expanding ever since, and as it expands, the matter within it spreads out, becoming less and less dense. The expansion of space itself increases the distances between objects, diluting the average density of matter throughout the cosmos. Gravity works against this dilution by pulling matter together into clumps. Regions that were slightly denser than average in the early universe attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to the denser regions and became emptier. Over billions of years, this process created the structure we see today. Matter concentrated into stars, which are concentrated into galaxies, which are concentrated into galaxy clusters and superclusters, with vast voids between them. But even with gravity concentrating matter into structures, the vast majority of space remains empty because the fundamental ratio of matter to space is so low. If you took all the matter in the observable universe, every atom in every star, planet, gas cloud and galaxy, and spread it uniformly throughout all of space, the density would be about 5 atoms per cubic meter. This is the average density of the universe, and it reveals that matter is extremely rare. The universe is about 5 atoms of matter per cubic meter on average, with the rest being empty space and dark energy. The emptiness of space has profound implications. It means that collisions between stars are extraordinarily rare, even in the centers of galaxies, where stars are most densely packed. When two galaxies collide, and galaxy collisions are fairly common on cosmic timescales, the stars themselves almost never hit each other. The galaxies pass through each other, like two clouds of gnats interpenetrating, without individual gnats colliding, because the distances between stars are so large compared to the stars' sizes. The emptiness also means that space travel is, in some ways, easier than it might otherwise be. A spacecraft travelling through space doesn't need to constantly dodge debris or navigate through fields of material. Space is clear. The challenges of space travel come not from crowding but from the vast distances between destinations and the energy required to cross those distances. Light from distant objects travels through this emptiness for billions of years, crossing intergalactic voids, interstellar space, and the relative crowding of planetary systems to eventually reach our telescopes. The fact that we can see distant galaxies at all, objects billions of light years away, testifies to how empty space is. If space were filled with gas or dust at densities even remotely approaching terrestrial conditions, the light would be scattered and absorbed long before travelling such distances. The emptiness of space is not a coincidence or an accident. It's a fundamental consequence of the universe's expansion, the initial density of matter after the Big Bang, and the way gravity organises that matter into structures. The spectacular images of galaxies, nebulae, and star clusters show us the rare locations where matter has concentrated. But these are the exceptions, the islands of matter in an ocean of emptiness. The typical state of the universe is not the crowded star field or the dense nebula. It's the dark, cold, nearly perfect vacuum of intergalactic space, where a single atom might drift alone for years before encountering another, where the nearest star is so distant that its light takes millions of years to arrive, and where the overwhelming reality is not presence but absence, not matter but void, not something but nothing, extending in all directions for distances that dwarf the span of human comprehension. Why some objects in space are heavier than others. When you hold a rock in one hand and a piece of styrofoam the same size in the other, the difference is immediately obvious. The rock is heavier. This difference comes from density, the amount of mass packed into a given volume. The same principle operates throughout the universe, but on cosmic scales, the variations in density become far more extreme than anything we encounter in daily life. Understanding why some objects in space are heavier than others means understanding how matter behaves under different conditions of temperature, pressure, and gravity, and how the history of an object determines what it's made of, and how tightly that material is packed together. Start with the simplest objects in space, clouds of gas in the interstellar medium. These clouds are extraordinarily diffuse, containing perhaps only a few atoms per cubic centimetre. In comparison, the air you breathe contains about 25 billion molecules per cubic centimetre. The density of interstellar gas is so low that the best vacuum we can create on Earth is still millions of times denser. These gas clouds have mass, sometimes thousands or even millions of times the mass of the Sun, but it's spread across such enormous volumes that the density is essentially zero by any terrestrial standard. Planets show a wide range of densities depending on their composition and formation history. The gas giants Jupiter and Saturn are primarily hydrogen and helium, the lightest elements. Jupiter's average density is about 1.3 grams per cubic centimetre, only slightly denser than water. Saturn is even less dense at 0.7 grams per cubic centimetre. It would float in a bathtub if you could find one large enough. This low density reflects their composition, dominated by the lightest elements in the universe, compressed by their own gravity, but not enough to create extremely high densities. The rocky planets of the inner solar system are much denser. Earth has an average density of 5.5 grams per cubic centimetre, about 4 times denser than Jupiter, despite being much smaller. This difference comes from composition. Earth is made primarily of rock and metal, silicates in the mantle and crust, iron and nickel in the core. These materials are intrinsically denser than hydrogen and helium. Silicon, oxygen, magnesium, and iron atoms are much more massive than hydrogen atoms, and when they bond together into minerals and metals, they pack together more tightly than gases can. Mercury, the innermost planet, is even denser than Earth at 5.4 grams per cubic centimetre, despite being much smaller. For a small planet, this density is surprisingly high, and it tells us that Mercury must have an unusually large iron core relative to its size. The leading theory, developed by planetary scientists studying how planets form, suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core, with only a thin shell of rock surrounding it. The iron, being much denser than rock, gives Mercury its high density. White dwarfs represent a dramatic jump in density. These are the remnants of stars like the Sun after they have exhausted their nuclear fuel and shed their outer layers. What remains is the core, compressed by gravity but supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth, creating densities around 1 million grams per cubic centimeter, or 1 metric ton per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This represents matter compressed to the point where atomic nuclei are essentially touching, with electrons flowing between them in a degenerate electron gas. Subramanian Chandrasekhar calculated in the 1930s that there's a maximum mass for white dwarfs, about 1.4 times the Sun's mass, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and further collapse occurs. This calculation, which earned Chandrasekhar the Nobel Prize decades later, explained why some stellar remnants become something even denser than white dwarfs. Neutron stars take density to an even more extreme level. When a massive star's core collapses in a supernova, if the core's mass exceeds the Chandrasekhar limits, but is below about 3 solar masses, it compresses beyond the point where electron degeneracy can support it. The electrons are forced into the protons, combining through inverse beta decay to form neutrons. The result is a neutron star, a sphere about 12 miles across containing 1 to 2 solar masses. The density at a neutron star's center reaches about 500 million to perhaps 1 billion tons per cubic centimeter. This is comparable to the density inside an atomic nucleus, meaning a neutron star is essentially a single gigantic nucleus held together by gravity rather than the strong nuclear force. At these densities, matter behaves in ways impossible to replicate in laboratories. The neutrons exist in a superfluid state with zero viscosity. The outer crust is a crystalline lattice of neutron-rich nuclei. Deeper down, neutrons drip out of nuclei and flow freely. At the very center, densities might exceed that of atomic nuclei, and matter might transition into exotic states, quark-gluon plasma, where neutrons dissolve into their constituent quarks, or other forms of matter predicted by quantum chromodynamics, but never observed. Black holes represent the ultimate extreme of density, though their density is somewhat paradoxical. The matter that forms a black hole collapses to a singularity, a point of infinite density, where general relativity predicts that space-time curvature becomes infinite. The singularity is hidden behind the event horizon, and we can meaningfully talk about the average density within the event horizon. For stellar mass black holes formed from collapsed stars, this average density is extraordinarily high, but for supermassive black holes containing millions or billions of solar masses, the event horizon is so large that the average density within it can be quite low, sometimes less than water for the largest black holes. This doesn't mean the black hole's interior is actually that density, just that if you calculated density by dividing total mass by the volume enclosed by the event horizon, you would get that number. The density variations we observe in the universe reflect the different physical processes that create and shape cosmic objects. Gas clouds have low density because gravity hasn't compressed them significantly. Thermal pressure from their temperature balances gravity, maintaining their diffuse state. Planets have intermediate densities determined by their composition, which depends on where they formed in the protoplanetary disk and what materials were available. Rocky planets formed close to their stars where it was too hot for ices to condense, while gas giants formed farther out, where ices could exist and helped build massive cores that captured hydrogen and helium. Stellar remnants have high densities because they are supported not by thermal pressure, but by quantum mechanical degeneracy pressure. As physicist Wolfgang Pauli explained in formulating the exclusion principle in 1925, fermions, particles like electrons and neutrons, cannot occupy identical quantum states. When you try to compress them, they resist because there are no available quantum states for them to occupy. This quantum pressure can support matter to much higher densities than thermal pressure can, but only up to certain limits determined by the mass and the type of fermion providing the support. Temperature also affects density. Hot gas is less dense than cold gas at the same pressure because the particles move faster and push outward more strongly. This is why hot air rises. It's less dense than the cooler air around it. In space, hot gas in the coronas of stars or in galaxy clusters has lower density than cooler gas in molecular clouds, even when both regions have similar pressures. The Sun's core, where temperatures reach 27 million degrees Fahrenheit, has a density of about 150 grams per cubic centimetre, dense by terrestrial standards, but far less dense than a white dwarf, even though the Sun's core is much hotter. The difference is that the Sun is supported by thermal pressure from ongoing nuclear fusion, while a white dwarf is supported by electron degeneracy pressure after fusion has ceased. Composition fundamentally determines the density any object can achieve under given conditions. Hydrogen, the lightest and most abundant element, naturally produces lower density objects than heavier elements. This is why gas giants, primarily hydrogen, are less dense than rocky planets made of silicon, oxygen, and iron. But composition interacts with pressure in complex ways. Under the extreme pressures inside Jupiter, hydrogen is compressed into a metallic state, denser than solid hydrogen would be under normal conditions, though still less dense than rock or metal. The formation history of an object determines both its composition and its density. Early in the solar system's formation, different materials condensed at different temperatures as the protoplanetary disk cooled. Close to the Sun, only metals and rocks could condense. These became the rocky planets. Farther out, where temperatures were lower, water ice could condense, providing additional solid material that helped build larger cores. These larger cores could then capture hydrogen and helium gas before the solar wind swept it away, forming gas giants. Farther still, at the coldest reaches, methane and nitrogen ices could condense, contributing to objects like Pluto and other Kuiper Belt objects. The history of compression matters too. Jupiter's core is thought to be compressed rock and ice, squeezed by the weight of the hydrogen and helium above it, to pressures millions of times Earth's atmospheric pressure. Under these conditions, materials that started as ordinary rock and ice are compressed to much higher densities, possibly exceeding even the density of iron under normal conditions. The exact state of matter under such extreme pressures remains uncertain. Laboratory experiments can replicate some of these conditions, but not the combination of extreme pressure, temperature, and scale found in giant planet interiors. Rotation affects density distributions within objects. A rapidly spinning object experiences centrifugal forces that cause it to bulge at the equator and flatten at the poles. This changes the density distribution, making the equatorial regions less dense and the polar regions denser. Saturn, spinning rapidly and composed largely of fluid, shows a noticeable oblate shape. Its equatorial diameter is about 10% larger than its polar diameter. Neutron stars spinning hundreds of times per second bulge significantly at their equators, altering their density distributions and affecting how they emit radiation. Throughout the universe, from the near vacuum of intergalactic space containing less than 1 atom per cubic meter, through the varied densities of planets, stars, and stellar remnants, to the extreme densities of neutron stars and the singularities within black holes, density varies by factors of hundreds of billions of billions. These variations reflect the different conditions under which matter exists. The temperatures, pressures, compositions, and quantum mechanical states that determine how tightly matter can be packed together, creating the extraordinary range of cosmic objects we observe, each with its own characteristic density, telling the story of how it formed and what forces shape its structure. Why space looks black. When astronauts look out the windows of the International Space Station, they see a view that never fails to inspire awe. Earth below with its blue oceans and swirling white clouds, and beyond it, the blackness of space dotted with brilliant points of starlight. That darkness seems natural and expected. Space is far from the sun, far from Earth's atmosphere, so of course it's dark. But this simple explanation masks a puzzle that perplexed astronomers for centuries. If the universe is infinite and filled with stars in every direction, then no matter where you look, your line of sight should eventually hit a star. The entire sky should blaze with light, as bright as the surface of the sun in every direction. Yet space is dark. This contradiction, known as Olbers' paradox after the German astronomer who popularized it in the 19th century, reveals deep truths about the universe's nature, age, and evolution. The puzzle seemed straightforward to early astronomers. Imagine the universe extends forever in all directions, filled uniformly with stars. Draw an imaginary sphere around Earth at any distance. That sphere contains a certain number of stars. Now draw a larger sphere at twice the distance. This larger sphere has 4 times the surface area, so it contains 4 times as many stars. Each individual star appears fainter because it's farther away. Brightness decreases with the square of distance, but there are 4 times as many stars, exactly compensating for their individual faintness. Every shell at every distance contributes the same amount of light. If the universe is infinite, there are infinitely many such shells, so the total light should be infinite. The night sky should be blindingly bright. Clearly, this doesn't match what we observe. The night sky is dark except for individual stars, planets, and the faint band of the Milky Way. Something must be wrong with the reasoning. Early astronomers proposed various solutions. Perhaps dust between stars absorbs starlight, darkening distant regions. But this doesn't really solve the problem. The dust would heat up from absorbed starlight and would eventually glow just as brightly as the stars themselves. Perhaps stars aren't distributed uniformly, with empty voids creating dark patches. But if the universe is infinite and eternal, stars should exist everywhere eventually, filling in any voids given enough time. The true solution involves the universe's finite age and its expansion, concepts unknown when Olbers formulated his paradox. The universe is not infinitely old. It began roughly 14 billion years ago in the Big Bang. Light travels at a finite speed, so we can only see light from objects whose light has had time to reach us since the universe began. The observable universe has a boundary, not a physical edge, but a horizon beyond which we cannot see, because light from more distant regions hasn't had enough time to reach us yet. This finite light travel time alone would solve Olbers' paradox, even if the universe weren't expanding. There simply aren't infinitely many stars visible. Only those within about 14 billion light-years, the distance light can travel in the age of the universe. This limits the total amount of starlight reaching us to a finite value, much less than would be needed to make the sky bright everywhere. But the universe's expansion adds another crucial element. Distant galaxies are receding from us as space itself expands. This recession causes their light to be redshifted, stretched to longer wavelengths. Light that left a distant galaxy as visible or ultraviolet radiation arrives, at Earth shifted into infrared or even microwave wavelengths. Our eyes cannot detect infrared or microwave light, so this redshifted radiation doesn't contribute to the visible brightness of the sky. The farther away a galaxy is, the faster it's receding, and the more severely its light is redshifted. The most distant galaxies we can observe have their visible light redshifted so far that it arrives as infrared or even radio waves. The cosmic microwave background radiation demonstrates this effect perfectly. This radiation, released when the universe was only about 380,000 years old, fills all of space uniformly. When it was emitted, it was visible and infrared light with a temperature of about 3,000 degrees. But in the billions of years since then, the universe has expanded by a factor of about 1,100. The wavelengths of this radiation have been stretched by the same factor, shifting what was once visible light into microwave wavelengths. The temperature corresponding to this radiation has dropped to less than 3 degrees above absolute zero. If we had eyes that could see microwaves, the sky would glow uniformly in every direction with this faint microwave light. But in visible light, it contributes nothing, leaving the sky dark. Another factor contributing to the darkness of space is the finite lifespan of stars and galaxies in their current bright state. Stars don't shine forever. They exhaust their fuel and fade. The universe's star formation rate was higher in the past and is declining now as gas is used up. In the far future, the universe will contain many more dead stellar remnants than active shining stars. Even if the universe were infinitely old, which it isn't, the sky might still be dark because most stars would have long since burned out. The darkness also depends on perspective. From Earth's surface, the atmosphere scatters sunlight, making the daytime sky bright blue and the nighttime sky somewhat illuminated by air glow and scattered artificial light. In space, without atmosphere to scatter light, the sky appears black in all directions, except where you're looking directly at a light source. Sunlight doesn't fill space with general brightness the way it illuminates Earth's atmosphere. Light travels in straight lines, and unless it's scattered or reflected by something, it remains invisible. You can be in bright sunlight in space, with the sun illuminating your spacecraft, but when you look away from the sun, you see only darkness and stars. The blackness of space also reveals something about the nature of light and vision. We see objects because they emit or reflect light into our eyes. Empty space contains no particles to scatter or reflect light, so there's nothing to see. It appears black. This is different from looking into a dark room on Earth, where at least some scattered light usually reveals dim shapes. Space between stars is truly empty of matter, with typically less than 1 atom per cubic centimetre. With so few particles to interact with light, the light simply passes through unaffected, leaving space black. Interstellar dust does exist, and it does affect starlight, but not enough to solve Olber's paradox. The dust absorbs and scatters light from stars behind it, causing extinction, making those stars appear fainter or invisible. This creates the dark dust lanes visible in photographs of the Milky Way and other galaxies. But the dust also glows faintly in infrared light from absorbed stellar radiation. The net effect is to redistribute light from visible to infrared wavelengths, not to eliminate it entirely. Even in regions with many visible stars, the spaces between them remain black. The Orion Nebula, one of the brightest nebulae visible to the naked eye, appears as a glowing cloud because gas in the nebula fluoresces in response to ultraviolet light from young hot stars within it. The gas absorbs ultraviolet light and re-emits it as visible light, making the nebula glow. But between the glowing gas clouds, space remains dark. Only where matter exists to interact with light does the light become visible. From certain perspectives, space isn't quite black. Sensitive instruments can detect faint glows from various sources. Zodiacal light, caused by sunlight reflecting off dust particles in the inner solar system, creates a faint glow along the ecliptic. Airglow from Earth's upper atmosphere creates a faint luminescence visible from orbit. The integrated starlight from billions of faint, unresolved stars creates a faint background glow called the extragalactic background light. But these glows are extraordinarily faint, thousands of times dimmer than the darkest sky visible from Earth's surface, and our eyes cannot detect them. To human vision, space appears black. The darkness of space has practical implications for astronomy. Because space is black, stars and other objects stand out clearly against the background without competing light washing them out. The best ground-based telescopes are built on remote mountaintops, far from city lights, precisely to take advantage of darker skies. But even the darkest Earth-based sight cannot match the blackness of space, where no atmosphere scatters light and where the sky is dark even in the direction of the sun. This darkness also affects spacecraft and astronaut safety. On the shadowed side of Earth or another planet, or in the shadow of the spacecraft itself, darkness is absolute, except for starlight. Astronauts working in shadow must use artificial lights because the starlight alone is far too faint to see by. The contrast between brilliant sunlight and deep shadow is extreme, creating challenges for cameras and human eyes trying to see details in both bright and dark areas simultaneously. The question of why space looks black connects to the deepest questions about the universe's structure and history. Space is dark because the universe had a beginning, because it's expanding, because light travels at a finite speed, and because stars have finite lifetimes. If any of these factors were different, if the universe were infinitely old and static, for instance, the sky would not be dark. The darkness itself is evidence for the Big Bang, for cosmic expansion, for the finite age of the universe. Every time you look up at the night sky and see darkness punctuated by stars rather than a uniform blaze of light, you're seeing direct evidence that the universe had a beginning, that it's been expanding for billions of years, stretching the light from distant sources into wavelengths your eyes cannot detect, leaving the spaces between stars as dark voids that reveal the fundamental nature of the cosmos through their very emptiness. Why silicon-based life forms might be possible. For as long as scientists have contemplated life beyond Earth, one element has persistently captured imaginations as a possible alternative to carbon: silicon. Science fiction has explored silicon-based aliens in countless stories, from rock-like creatures that metabolize minerals to crystalline beings that think at geological timescales. But these fictions rest on a foundation of genuine chemistry. Silicon sits directly below carbon in the periodic table, shares many of carbon's most important properties, and is far more abundant in Earth's crust than carbon. Yet despite this abundance and chemical similarity, silicon never became the basis for life on Earth. Understanding why silicon-based life might still be possible elsewhere requires examining both the remarkable parallels between silicon and carbon chemistry and the significant obstacles that would need to be overcome. Carbon's dominance in biochemistry stems from several key properties. Carbon atoms can form 4 strong covalent bonds with other atoms, allowing them to link together into chains, branches, and rings of almost unlimited complexity. A single carbon atom might bond to 4 other carbon atoms, creating a 3-dimensional network. Or carbon atoms might link into chains hundreds or thousands of atoms long, with various other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, attached at different positions. This versatility allows carbon to form millions of different molecules, from simple methane with 1 carbon atom to DNA molecules containing billions of carbon atoms arranged in precise sequences that store genetic information. Silicon shares carbon's ability to form 4 covalent bonds. The electron configuration that gives carbon its bonding properties is mirrored in silicon, making silicon capable of forming similar structures: silicon chains, silicon rings, silicon networks. In fact, silicon chemistry forms the basis of an entire class of synthetic materials called silicones, which consist of chains of alternating silicon and oxygen atoms with organic groups attached. These materials, familiar as sealants, lubricants, and medical implants, demonstrate that silicon can indeed form large complex molecules. But silicones are human inventions, created in laboratories and factories. Nature has not produced silicon-based organisms, at least not on Earth, despite silicon being about 900 times more abundant in Earth's crust than carbon. The primary obstacle to silicon-based life under Earth-like conditions is silicon's relationship with oxygen. When carbon reacts with oxygen, when it burns, it forms carbon dioxide, a gas at normal Earth temperatures. This gas can be easily expelled from an organism and recycled back into the environment. Plants take in carbon dioxide and use it to build sugars through photosynthesis. Animals exhale carbon dioxide as a waste product of metabolism. Carbon dioxide dissolves readily in water, allowing it to be transported in blood and participate in various chemical reactions. The carbon cycle that sustains Earth's biosphere depends on carbon dioxide being gaseous, mobile, and chemically accessible. Silicon's equivalent compound is silicon dioxide, silica, quartz, sand, rock. When silicon burns with oxygen, it forms a solid. This solid is extremely stable, nearly insoluble in water, and chemically unreactive under normal conditions. An organism that metabolizes silicon and oxygen the way Earth organisms metabolize carbon and oxygen would accumulate solid mineral waste inside its body or would need to excrete sand. The waste products of silicon metabolism cannot easily be transported in fluids, cannot be exhaled as gas, and cannot be recycled through environmental cycles the way carbon dioxide can. This fundamental difference makes silicon-oxygen chemistry poorly suited for biochemistry on worlds with oxygen-rich atmospheres and liquid water. However, removing oxygen from the equation changes the possibilities dramatically. In environments where oxygen is absent or rare, silicon chemistry behaves very differently. Silicon forms stable bonds with hydrogen, creating silanes, molecules analogous to hydrocarbons, but with silicon replacing carbon. The simplest silane is silane itself, with one silicon atom bonded to 4 hydrogen atoms, analogous to methane. Longer chains are possible, disilane with 2 silicon atoms, trisilane with 3, and so on. These silicon-hydrogen chains are reactive and unstable compared to carbon-hydrogen chains, but in the absence of oxygen, they might persist long enough to serve biological functions. Temperature plays a crucial role in silicon chemistry. At Earth's surface temperatures, silicon-silicon bonds are relatively weak compared to carbon-carbon bonds. Silicon compounds tend to break apart more easily, making long, stable silicon chains difficult to maintain. But at much colder temperatures, the kinds found in the outer solar system, silicon chemistry becomes more favorable. Chemical reaction rates slow down dramatically at low temperatures, which could actually help stabilize silicon compounds that would rapidly decompose at room temperature. Meanwhile, some of the alternative solvents that might replace water at these temperatures could interact with silicon compounds in ways that favor complex chemistry. Liquid methane and ethane, which exist naturally on Saturn's moon Titan at temperatures around -180 degrees Celsius, represent one possibility. In these hydrocarbon seas, water is as hard as rock and oxygen is locked away in ice and minerals. Silicon compounds might dissolve in liquid hydrocarbons more readily than in water, and without oxygen to react with, silicon could potentially form the complex, diverse molecules that life requires. The chemistry would be radically different from Earth's biochemistry. Reaction rates would be thousands of times slower, molecules would have different shapes and properties, and the fundamental mechanisms of energy storage and information transfer would need to be reimagined. But the basic requirements for life, complex molecules that can store information, catalyze reactions, and self-replicate, might still be achievable with silicon as the central element. Liquid nitrogen, which exists at even colder temperatures, offers another potential solvent. Nitrogen becomes liquid at -196 degrees Celsius at Earth atmospheric pressure. A world with lakes or oceans of liquid nitrogen would be incomprehensibly cold by Earth standards, but chemical reactions would still occur, just very slowly. Silicon compounds might be more stable and diverse at these extreme temperatures, allowing them to form the kinds of complex structures that life needs. Another approach to silicon-based life involves thinking beyond complete replacement of carbon. Instead of imagining organisms built entirely from silicon, consider hybrid biochemistries that use both elements. Silicon might form structural components, while carbon handles information storage and catalysis. Silicon-oxygen minerals could serve as skeletal elements, providing rigid support structures that carbon-based soft tissues attach to. This is essentially what Earth organisms do. Bones, shells, and the glass-like structures of diatoms all incorporate silicon compounds, though the fundamental biochemistry remains carbon-based. A true silicon-based organism would integrate silicon more deeply into its biochemistry, perhaps using silicon-containing molecules for energy storage, membrane structure, or even genetic material. The information storage challenge represents one of the most significant hurdles for silicon-based life. DNA and RNA work remarkably well as information storage molecules because they're stable enough to preserve information over time, but flexible enough to be copied and modified. The sugar-phosphate backbone provides structural support, while the nitrogen bases store actual information through their sequence. Could silicon replace the carbon in the sugar molecules? Silicon-containing analogues of sugars and nucleotides have been synthesized in laboratories, demonstrating that such molecules can exist. Whether they could reliably store and transmit information across generations in a living organism remains unknown, but the chemistry doesn't appear to forbid it outright. Energy metabolism in silicon-based organisms presents another puzzle. Earth organisms primarily extract energy by rearranging chemical bonds, breaking bonds in food molecules, and forming new bonds in waste products, capturing the released energy in the chemical bonds of ATP. Silicon-based organisms would need analogous processes. Perhaps they could oxidize silanese to release energy, though the solid silicon dioxide waste product would be problematic. Or they might use entirely different metabolic pathways based on silicon's interaction with halogens like fluorine or chlorine, creating different waste products that could be more easily managed. In extremely cold environments, metabolic rates could be extraordinarily slow. A silicon-based organism might take years to grow or reproduce, operating on timescales that would make watching grass grow seem rapid by comparison. The evolution of silicon-based life would require a planet with very specific conditions. Silicon would need to be available in reactive forms rather than locked into stable minerals. The temperature would probably need to be very cold to favor silicon chemistry over its tendency to decompose. Oxygen would need to be absent or rare to prevent silicon from forming insoluble silicon dioxide. A suitable solvent other than water would need to exist: liquid hydrocarbons, liquid ammonia, or something even more exotic. These conditions might exist on certain moons in the outer solar system, on rogue planets drifting through interstellar space, or on exoplanets orbiting dim red dwarf stars, where temperatures never rise above the freezing point of water. Titan, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its extremely cold temperatures, represents perhaps the best candidate in our solar system for silicon-based life. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will explore Titan's surface and could potentially detect signs of exotic biochemistry if it exists. The mission won't specifically look for silicon-based life. Nobody knows exactly what signatures such life would produce, but it will analyze organic chemistry in Titan's lakes and atmosphere. searching for patterns that might indicate biological processes. Even if silicon-based life exists nowhere in the universe, studying the possibility expands our understanding of chemistry's relationship to biology. It forces us to question our assumptions about what life requires and what forms it might take. Every element brings different properties, different strengths and weaknesses, different possibilities and constraints. Carbon happened to be the element that worked on Earth under Earth's conditions, but Earth represents just one set of conditions among countless possibilities across the universe. The theoretical possibility of silicon-based life also highlights a challenge in searching for extraterrestrial life. Most of our detection methods assume life will be similar to Earth's, producing oxygen, methane, or other gases we associate with biological activity, building structures we would recognize using chemistry we understand. But silicon-based life operating in liquid methane seas at -180 degrees Celsius would produce completely different signatures. It might metabolize compounds we consider inert waste products and excrete substances we consider essential for life. Its waste products might be our nutrients, and vice versa. We might look directly at a world covered in silicon-based organisms and not recognize it as inhabited because we're searching for carbon signatures. Silicon-based life might be possible in environments so different from Earth that the very definition of life becomes strained. Perhaps silicon-based entities would be better described as self-organizing chemical systems rather than organisms in any sense we would recognize. They might grow and reproduce on timescales of centuries. Their metabolism so slow that a single thought, if they think at all, might take years to form. They might not have discrete bodies with clear boundaries between self and environment, but instead exist as diffuse networks of silicon-based chemistry spread across vast areas. They might not die in any meaningful sense, but simply cease maintaining organization and gradually disperse back into their environment. Why silicon-based life forms might be possible comes down to chemistry being flexible, creative, and opportunistic. The laws of chemistry operate everywhere in the universe, but they produce different outcomes under different conditions. Silicon's chemical properties give it potential as a basis for complex, self-organizing systems under the right circumstances. Circumstances that apparently don't exist on Earth, but might exist elsewhere. From the hydrocarbon lakes of Titan to hypothetical ice worlds, orbiting dim stars to environments we haven't yet imagined, silicon might be constructing molecules, storing information, and powering metabolisms in ways that parallel carbon-based life, just enough to recognize as living while remaining alien enough to challenge everything we thought we knew about biology, proving that life's possibilities extend beyond the single example we know to encompass chemistries as diverse as the cosmos itself.